algorithms in the last class, and we saw one particular algorithm for vertex cover. This algorithm was quite simple. You start with your graph, take any edge, take both vertices in your vertex cover, and remove all edges that these two vertices cover. Once you have done this, the graph is a smaller graph, some edges are gone, so you just repeat this process. So pick another edge, pick the two vertices at the two ends of the edge and repeat. Okay? So that was, and we saw that in fact for this particular algorithm, the cost of the optimal solution, or the number of vertices in the optimal solution, is at least half times the number of vertices that the algorithm selects in its vertex cover. Okay? And we call this the approximation factor of the algorithm, the worst case ratio between the value of the objective in the algorithmic solution to the value of the objective in the optimal solution. So this was called the approximation ratio. This is a minimization problem. So we are taking when we say worst case, we mean the maximum possible ratio. If this were a maximization problem, then you would be taking the minimum ratio, okay, overall. So this is the general notion of approximation, and today we'll go a little deeper into what approximation means, or we'll see a few more examples of approximation algorithms. The first example we'll see will be along the lines of vertex cover in terms of the algorithm that we will use, but the analysis will be somewhat different. So this is a problem called set cover. Okay, so the set cover problem is a generalization of vertex cover. Okay, so vertex cover is a special case, and when I define the problem, we'll see that in fact vertex cover can be represented also as a set cover problem. So what is this problem? So you have a universe of elements. Okay, let's call it X, and you have a collection of subsets of X. So there are a bunch of sets S1 through Sm, where Si or any I is in fact a subset of S. Okay, so you have a universe of elements and a collection of subsets, and your goal is to select the minimum number of subsets let's say the selection is in a set of subsets called T. So you want to select the minimum number of subsets such that they cover all the elements. So if I take a union over all these subsets that we have selected, let's say union over Si belongs to T, then this should be equal to X. Okay? So you are given a universe of elements. You are given a bunch of subsets on that universe, and you will denote the number of elements by n. So let's say size of X is n. You are given a bunch of subsets on these elements on this universe, and what you want to do is to select some sub-collection of subsets, okay, some of these subsets, such that their union is in fact X, and you want to minimize the number of subsets that you have selected. Okay, so let's take an example. So let's say X equals 1, 2, and 3, and we have a few subsets. Okay. Suppose I have these 4 subsets. Let's put one more in. So we have these 5 subsets. So what is the optimal answer here? How many subsets do I need to select such that all these elements are picked? 2 subsets, right? So for example, I could either pick this and this, or I could pick this, and both of these are optimal. Because I'm picking 2 subsets, and there's no way of picking just one subset and covering all the others. So this is the set cover problem. And I claim that this is a generalization of vertex cover. Why? Why can vertex cover be represented as a particular case of a set cover problem? every set comprises a single node, and then how are your subsets, and then what are you covering? So the point is, note that you have to cover all the elements of the universe. So in vertex cover, what are you covering? All the edges, right? So really X should represent the set of edges. And what should be the sets?
All the edges that you can add a node.
Exactly. So every set should correspond to a node, as we were saying, which basically means that for a particular set, for any set, it comprises the set of edges that are incident on that node. Okay. So that will represent picking the set and covering all the edges incident on the node. Is that clear? So vertex cover is in fact a special case of set cover, and therefore that immediately says that set cover is also NP hard. But it turns out that set cover in fact is harder. Okay, in what sense? In the sense that we cannot hope to get a too approximate algorithm, unlike in the case of vertex cover. Okay, this is well beyond the scope of this class. I won't show you why it's essentially impossible to get a too approximate algorithm for set cover. But what we'll see is some other algorithm which will get a weaker approximation ratio. The approximation ratio will be bigger. So it's not as good as the too approximate algorithm for vertex cover, but it will apply to this much more general problem that we are calling set cover. Okay? So what is the most naive algorithm that you can think of for set cover? What's the first algorithm that you will try?
Well, if you pick all the subsets.
Okay. You could pick all the subsets, and that's a feasible solution that will cover all your elements. If that's not covering all your elements, then you're in big trouble. So clearly that's a good algorithm in the sense that it's producing a feasible solution, but that could be terribly far away from the optimal, right? So for example, if there is one subset which contains the entire universe, right? There could be a single subset containing the entire universe. In that case, picking all the subsets is actually has an approximation factor of. So imagine that there's one subset Si that is in fact equal to X. Then what is the approximation factor if I pick all the subsets?
M.
It's M, right? It's this number, the number of subsets I'm picking. I could have just picked one subset, I'm picking all of them. So that's quite bad. We don't want the approximation factor to be that bad. We can do something better. So what are other options? What kind of algorithms can we run?
Choose the largest subset first.
We repeat the
largest subset first.
We'll take the largest subset first. Okay? Okay. Even before that, what's a naive? So we saw a very naive algorithm which gives an approximation factor of M. What is a naive algorithm which gives an approximation factor of N, the number of elements? Well, one thing I could do is I take every element and I simply pick an arbitrary subset that contains the element. Okay, and throw all these subsets in. Now how many subsets am I picking? I'm picking n subsets. The optimal solution needs to pick at least one subset. So clearly the approximation factor of that algorithm, which picks one subset for every element, is n. Okay, so getting an approximation factor of m or getting an approximation factor of n are relatively easy. And now we will improve this significantly by in fact getting an approximation factor of log n. Okay, so it's exponentially better. And in fact, that's the best we can do for this problem. So the algorithm we will use is the algorithm that you were suggesting. This is in some sense a natural algorithm. Someone asked you to code this up for some problem somewhere. The first algorithm we'll probably run is the following. I take the subset that's biggest. Okay, that seems the best choice currently for me. So I take the biggest subset that covers some set of elements. So I include the biggest subset in T. Now whatever elements it covers, I remove those elements from X and I repeat. So I again take the biggest subset that covers the maximum number of elements I haven't covered. Okay. So this is the natural greedy algorithm. Okay. So if I ran this algorithm on this example, what would I pick? So I start out by picking one of the largest subsets in the example. So which is the largest subset? Well, I could pick any of these two subsets. Let's say I pick this. Okay. So this is my first set. And now once I've picked it, I remove these 2 and 3 from the set of elements that I still need to cover. So the set of uncovered elements only contains 1. So now I could either pick this. So this is a subset which covers the only uncovered element left, or I could pick this. Okay, so this is the first subset, and then 2 could be the disassembly. Okay, any questions about what this algorithm is, how the algorithm runs? Good. So it's a relatively simple algorithm. There's not much complication. Question is, how do we analyze it? How good is this algorithm? So to analyze this algorithm, let's try to compare it with an imaginary optimal solution. So we don't know what the optimal solution is. This is only for the analysis. If you look at this description of the algorithm, the optimal solution hasn't shown up. Okay, and this is something you should keep in mind. So often in analysis, we will say that let the optimal solution be something and do some comparisons. But that's only for analysis. That's not in the algorithm. You can't write an algorithm saying that let the optimal solution be something and we'll base our algorithmic choices on what the optimal solution is doing. Because I don't know the optimal solution. Okay, this is only in hindsight. So let's say I have an optimal solution. This is my universe. And let me draw the optimal solution in black and the algorithmic solution in red. Okay? So the first set that the algorithm picks is some set like this. Okay, this is what the algorithm picks. Let's say the size of this set is n1. My first claim is that n1, so what is opt? Well, opt covers all the elements, but using some collection of sets that I don't know. Now my first claim is that n1 is at least n over opt. Okay? So what do we mean by this? By the way, when I say opt, I mean the value of the optimal solution. So this is the number of sets in the optimal solution. Okay, so my first claim is the number of elements in the algorithm's choice, the first set that the algorithm picks, is at least n over opt. Why is this true? So if the optimal solution had, let's say, 10 sets, then I'm saying that the number of elements in my first set is at least n over 10.
Because otherwise, n1 will not be the largest size.
Why not?
Because others, I mean, the second and third size will have like nice contribution to the total number of elements in the size. I mean, in the union of size. So the first one will have like the most amount of unique elements. I mean, we'll cover like most elements in it.
Okay, so let's try to rephrase that. So given that opt covers all the elements, all the n elements, and does so using only opt number of sets, okay, what is the size of the largest set in opt? Can we lower bound the size of the largest set in opt? Is at least what? Yeah.
N over
N over?
M.
Certainly at least N over M, but we can say something with using this value, this as well.
N minus opt minus 1.
Or OPP.
N over opt, right? Actually, let me use different notation just to make sure that we're not confused. So let's say let's call this T star. Okay? So this is the number of sets in all. So I'm claiming that the size of the largest set is at least N over T star. Why? There are T star sets in opt that cover all the N elements. Okay? So in the worst case, each element is covered by just one set. Even then, there are T star things that are covering all the N elements. So there's at least one thing, just by averaging, which is at least as large as this. Okay? Imagine that you have 100 elements. If I have 10 sets covering the 100 elements, then there's at least one set which covers 10 elements. Right? If all the sets cover 9 elements or less, then the 10 sets cannot cover more than 90 elements. So just by simple averaging, the fact that T star sets are covering N elements implies that there's one set which covers at least N over T star elements. Is this clear? Good. So now I claim that this is obvious. Why is this inequality now obvious?
Is the largest set in your solution can't be more optimal than the optimal solution.
Right. So this is the largest set in your solution. This is the largest set among all the sets that are given to you. So this is at least as large as any set that opt uses. Opt also uses these sets, right? It doesn't use any other set. So the fact that opt uses only these sets implies that the largest set among them should be at least as much as any set in opt. In particular, this set, the largest set in opt. Okay? Since you chose the largest set without considering any other parameter, your set is at least as large as any set in the system, in particular the largest set in opt. Okay? Any questions? Good. So that's the first step. Now what happens in the next step? And now things start getting interesting. So in the next step, the algorithm buys another set. And let's say it covers N2 new elements now. Okay? My claim now is that in fact N2 is at least N minus N1 over T star. Okay? Now, who wants to argue the claim? It's very similar to what I argued for the first set. So forget about these N1 elements.
Professor,
Yeah.
isn't it T star minus 1?
No. So forget about these N1 elements. How many elements do you have?
N minus N1.
N minus N1. Opt covers these elements using how many sets?
T star. T star.
T star sets, right? I can't say that opt covers it using T star minus 1 sets. It potentially covers, it takes all the T star sets to cover these elements. Okay? So opt covers all these elements using T star sets. So among just these elements, what is the largest set that opt has?
N2.
Among just these elements. Okay? So if I just remove these N1 elements, then what is the largest, since opt is covering these remaining elements using T star sets, opt must be using some set here that's covering at least so many elements among these uncovered elements. Okay? So you can now claim that the size of the largest set in opt intersect the n minus n1 elements, the elements that you did not cover in the first step. So let's write it as so this size is at least n minus n1 over t star. Again by the simple averaging argument. Since there are t star sets covering at least n minus n1 elements among elements that are uncovered after the first step, so there's at least one that covers in opt that covers at least so many uncovered elements. Okay? And what is your greedy algorithm doing? What is this algorithm doing? It's picking the set that covers the most number of uncovered elements, that covers the maximum number of uncovered elements. So in particular, it must be covering at least as many uncovered elements as this set in opt covers. Right? Because this is an option that this algorithm has. It could have picked this set, but maybe it found a better set, a set that covers more uncovered elements. So it covers, so the number of elements it covers in the second step is at least this much. Okay? So now you can guess what the third step is. What should the inequality for the third step be? How much should N3 be? So again, what is N3? N3 is the set number of elements that the algorithm covers in the third step. So this is N3. Okay, number of uncovered elements that the algorithm is covering in the third step. And this should be at least how much? So again, remove all the n1 elements, remove all the n2 elements. In what remains, opt still uses t star sets to cover them. So in particular, there's one set in opt that covers at least these many elements. Okay? And you can simply repeat the argument. So in general, the ith set that you pick will contain at least this number of elements. Okay? Now how do I turn this into a proof now? So how do I turn this into an approximation factor? So I got all these recurrences, right? I have claimed that n1 is at least so much, n2 is at least so much, and so on. How do I convert this into a proof, into an approximation factor? So one way to do that is to think of algo in the following way. So let's say algo runs for k steps. Okay, it keeps picking k. It picks k. It picks k different sets. Okay, so you can think of algo's cost as 1 k times. And every time it picks a set, it pays a cost of 1. Now let's take the first one and write that out as n1 times 1 over n1. And the second one we'll write it out as n2 times 1 over n2, and so on. Okay, so succinctly, we're summing over I ni times 1 over ni. But now we have a bound on 1 over ni. How much is 1 over ni? From this equation, I know that 1 over ni is at most the quantity written there. Right? So it's at most t squared divided by n minus this. I haven't done anything, I've just rewritten terms. Now look at the first term here. What is the first term saying? The first term in this sum is the following. It's t squared times n1 divided by n. Right? I can rewrite this as t squared times 1 over n summed n1 times. Okay? And then instead of taking 1 over n every time, I can take 1 over n, then 1 over n minus 1 till 1 over n minus n1 plus 1. Okay, I'm just looking at the first term here. Okay, I'm just looking at the first term. I took the first term. If you go back here, the first term is t star times n1 divided by n minus, and here it's a sum till 0, so there's nothing here. So it's just t squared times, t star times n1 over n. Okay, which is what you saw here. It's t star times n1 over n. Okay, the cross multiplication. So this term I've written it out in the following way. I've taken n1 and split it up into n1 ones. Now instead of keeping all these 1 over n's, I've constructed this trailing series. So I have started with 1 over n, then 1 over n minus 1, and so on. Now why is this bigger? Because all of these terms are individually bigger than the 1 over n's. I'm just decreasing the denominator. Okay? But if I do that, then what happens? So I take this and I say that it's sum over I, and then sum over j going from 0 to ni minus 1, 1 over n minus. So let's actually write it out. So you have a t star, and then you have 1 over n plus 1 over n minus 1 till 1 over n minus n1 plus 1. Okay, that's where the first term ends. But now the second term starts, and what's the first term in the second term? Right? If I did the same thing with the second term, what would have happened? So the second term was t star times n2 over n minus n1. Right? I could have written that out as t star times 1 over n minus n1 summed n2 times. Okay? And I could have done the same trick here. So this is less equal to t star divided by 1 over n minus n1 plus 1 over n minus n1 minus 1, and so on till 1 over n minus n1 minus n2 plus 1. Okay? Exactly the same trick. I take these terms, I split up this n2 into n2 ones, and then for each term I produce this trailing series instead of keeping the same denominator. I just keep decreasing the denominator. But now if you look at what happens if I put these together, you can see that I have created a continuous series. So I start at 1 over n. This first sequence ends at 1 over n minus n1 plus 1. Second one has started at 1 over n minus n1. Okay, this guy ends at n minus n1 minus n2 plus 1. The third one will start at 1 over n minus n1 minus n2. So I have a continuous set of terms now. First one ends here, the second one starts from exactly the next term. It starts from 1 over n minus n1. Okay, and it keeps going and it ends at n minus n1 minus n2 plus 1. And then the third one will start here. and so on. Okay, and this ends with 1. So by just rewriting these terms, I have created this continuous series. Now what is this? This is something you have seen earlier. It's the harmonic series of n terms. So this is T star times the harmonic of n terms. And how much is the harmonic series? How much does it evaluate to asymptotically? Again, I showed you a trick, right? How do you remember what the harmonic series evaluates to? Think of the continuous case. What is the integral of 1 over x? 4. Log of x, right? So the harmonic series will evaluate to O of log n. Because this is just discretized, the discretized form of integral 1 over x, nothing else. Okay? So now we have shown that the algorithmic solution, the number of sets that the algorithm picks, is at most T star times O of log n, where T star is the number of sets that the optimal solution picked. Therefore, the approximation ratio of this algorithm is log n. Any questions about how we showed this? We'll start playing with this a little bit, and we'll see that there are many different proofs of this fact using many different techniques. But do you understand this very basic proof? No questions? Good. Alright, so let's now try to prove this in a different way. Let's use charging to prove the same thing. So here's my universe. And the sets that my algorithm picks covers this universe. Now one way of counting the number of sets that I have is to do the following. So this was the first set, it covered some n1 elements. This was the second set, this was the third set, and so on. So one way of counting the number of sets is to say that I'll give a charge of 1 over n1 on every element that the first set covered. Okay? I'll give a charge of 1 over n2 to every uncovered element that the second set covered. So the second set covers n2 new elements. I give a charge of 1 over n2 to each of them. So if in this way I give a charge to every element, what's the total charge on the elements? So I'm taking, what's the charge on the elements in the covered by the first set? 1. What's the charge on the elements covered by the second set? 1 again, right? So the total charge on all the elements is exactly equal to the number of sets in my solution. Okay? So if I can bound the total charge, that will also be a valid bound on my approximation ratio. Because the total charge is exactly equal to the number of sets. So that's what we aim to do. Now how do we deal with the optimal solution? So there's also the optimal solution. Let's look at the optimal solution. Now in the optimal solution, there is no sequence in which the sets are picked. Okay, so there is no way for me to go for a charging scheme which uses this kind of a sequence. Note that this set the second set I picked could actually be covering some of the elements that I already covered as well. But I don't give them a charge because of the second set. I only give charge to the ones that are newly covered. Now the optimal solution does not have this structure. The optimal solution can overlap in ways that I cannot predict. Some overlap. So now in the optimal solution, what I say is that I'll take any element and I give it a charge. So let's say this is set S1 and this is set S2. Then this element gets a charge of 1 over S1 plus 1 over S2. Okay, so this set S1 gives it a charge of 1 over S1 and this set S2 gives it a charge of 1 over S2. Okay, this is how the optimal charging starts off. Now, in the first step, can I argue that the charge on any element here is smaller than the charge of any element in the optimal solution? So look at any element that's covered by the first set. Okay, it gets a charge of 1 over F1. I want to argue that that charge is in fact smaller than the charge on any element in the optimal solution. Why is that true? Yeah.
Well, N1 is at least as large as the largest set used in the optimal solution, and by the optimal solution charging, we'll add other things to that charge.
Exactly. So as we argued, N1 is at least as large as the largest set in the optimal solution. So what that means is that even if every element were to receive charge from only one set, even that charge, even if I just took any one of these terms, each of these terms are actually bigger than 1 over N1 because the sets are smaller. Okay? So in the first round, the charge on the algorithm on the elements being covered by the algorithm are in fact smaller than the charge on the elements being covered by the optimal solution. Alright? Now what happens in the second round? In the second round, this need not be true. Of course, it cannot be true throughout, right? Because if it's true throughout the run of the algorithm, then the algorithm is actually doing better than the optimal solution. That's not possible. So something interesting happens in the second round. So what happens is that now a bunch of elements are already covered by the algorithm. So now you don't compare the previous charging scheme to the charge that the algorithmic solution gets, but you do a recharging on these elements. What is your recharging? Well, you just imagine that these elements got blown away. These elements aren't there, and then just do the same charging. Okay, so for every set, you look at the number of elements that are outside this red zone, and you take that as your charge. So it's not 1 over S1 anymore, but 1 over S1 only of the portion that's outside the red zone. Okay? So once you have redone the charging, you can again make the same claim. And if you go through this argument, you will see that you will get exactly the same equations back. Okay? And you can get a factor of log n. So you can do this in various ways. In the next class, if we have time, we will also see how this can be analyzed using LPs. LPs don't seem to have anything to do with this algorithm, but it turns out that you can analyze this algorithm and get this factor of log n using LPs. So that's something we'll see later. But this is one of the most basic algorithms that's very, very widely used in all of computer science now. Okay? So it's good to know how this algorithm works and why it has a logarithmic approximation. Any questions about the set cover algorithm? Alright, good. So let's move on and let's go to a different kind of algorithm. On the other hand, if epsilon is in fact a constant, this is a very large constant, but it's a constant, and therefore this running time is polynomial. So again, is this notion clear? What do we mean when we say that the running time is polynomial if epsilon is a constant? So I cannot guarantee anything in terms of the dependence on 1 over on epsilon. Okay, the dependence can be terrible, as you can see here. However, if I fix this, if this was 0.01 or even